Hello everyone, welcome to my channel. So in this part 2, we're going to talk about the logistic regression. I think you guys are ready with your hand note because today I'm going to talk about a lot of math intuitions and also the Python code implementation along with its optimization technique. Okay, so let's dive into it, and I think you guys will like and subscribe as much as possible so that a lot of students can get their help from this particular video. Okay, so let's dive in, guys. So today's topic is logistic regression. As you understand, previously we talked about the linear regression. If you didn't watch, you have to watch this video because that video is really important for data analysis as well. I talked about a lot of stuff, so you must have to watch that part 1 as well. Now if you come to part 2, here it has some amazing thing for you. And logistic regression actually works better for binary classification, where it has like yes or no. If you want to classify based on some parameter, if this guy has some diabetes or not, if this guy has cancer or not, if you want to identify those two binary classes, yes or no, then the binary class then the logistic regression will perform much better because it is designed for like this. And the second is very scalable. It is very efficient for a computer to process, and as well as it can handle very large data sets. So it's quite scalable, efficient, and also it can handle large data sets. And the third one we have, it is linearly separable data. It's really useful when you can separate those two data linearly. The sigmoid function range here, as you can see, is the range between this 0 up to 1. As you can see, this is 1 is the highest probability and 0 is the lowest probability. There is two different classes, and these two are the two polarities, 0 and 1. 1 is suppose that this guy has some diabetes or some cancers or some predictions or any class. This guy, it is positive. And 0 is that this guy doesn't have this disease. Okay, so they are completely two different polarities. 1 is different polarity and 0 is another polarity. And it is defined by the sigmoid functions z is equals to 1 over 1 plus e to the power z. And be careful, it is e to the power minus z. So total it is 1 divided by 1 plus e to the power minus z. So if you draw the function, if you draw the graph, it would be like this. Okay, so the graph, to understand the graph is so important, and the equation is pretty similar to previous one. If you just check in the previous linear regression, I talked about it's y is equals to mx plus c for single linear regression, and for multivariate it is m1 x1 m2 x2 m3 x3, and the c is the intercept. You need to import all of those things into today's concept, which is z is equals to m1 x1 m2 x2 m3 x3, because we have multiple feature in our data set here. Soon you're gonna see this. And the x1 is the each individual features. These are the input features, x1 x2 x3. These are the column features, and we need to just multiply it with its weight for all of them, then we get the z value. So if I just show you in the, so now if I just go into paint application, here you will see how the sigmoid function is working. Okay, so if I draw the sigmoid function, it is just, if I just take it, look into it, it is similar to that. Okay, so if your data point is like here, okay, so if I make it zoom, and in the other point, suppose it's 0 point and it's 1 point. Okay, we have two class because this is binary, and sigmoid function works like this. And if I write the function, z is equals to 1 over 1 plus e to the power minus z. So what this z is actually, let's talk about it. So as I was talking about this, if you have this point, it means that this guy has diabetes, it's positive. If your data point is similar here, suppose here, okay, then it's negative, it's negative. Okay, and if your data point is like here, it's positive. So if your data point is like 0.5, then it won't answer. It will answer if your data point is greater than 0.5, then it will automatically predict as 1. You have this disease. Okay, if it is below 0.5, if it is below 0.5, if your predicted value is suppose 0.2, and you get 0.2, but in the mid position we have 0.5, this place we have 0.5. So 0.5 is bigger than 0.2, so your data point is here, which is like 0.2, then it will classify this thing as negative as well. Okay, and if your data point is like here 0.7, then it will classify as positive. Anything above 0.5 is positive, you have this disease. Anything above or anything below the 0.5 is regarded as the negative, you don't have this problem. In your real life data set, we have so many points would be here and so many points would be here. Okay, those would be your error, because no model is 100% perfect, and there would be some data that is not positive, and still it would be here, and that would be the error of your model. And there would be some data which is which would be predicted as 0. It means that you don't have this disease, but still it should be 0.2, but still it will show that it is greater than 5, which is 0.7. Okay, so this would be the error. So that's why your applications or your model would be around 80 to 90% accurate most of the time, but the 10% are this error. Okay, these are this error. It should be negative, but it will show that you will have this disease, so it will show 1. And in this case, as it should show it is above 0.5, it should be classified into 1, but it will show that no, you don't have this problem. So these are some errors, and we will talk about how we can improve the accuracy of the logistic regressions. So that is the thing we are talking about, linearly separable data. So that is the reason sigmoid function is really important. And one more thing is that we talked about 1 over e plus 1. We talked about 1 divided by 1 plus e to the power minus z. What is this z? Z is actually the values of your features and weight. This is your coefficient along with its input feature, and another coefficient with its input feature x2. It can be up to n. Okay, wn, xn plus your intercept c. So if you put the value here, it would be 1 over 1 plus e to the power minus w1 x1 plus, it would be like that, plus w2 x2, this kind of thing. So it will give you the value, and we do this sigmoid function to convert the data into 0 up to 1. So whatever the value of w and xn, suppose its value is 10 times individual value is 2, this is the variable, plus then we have a weight of 20, then the individual value is 4, so this is 20 plus 80, so 100. But we don't want this, we want the value to be up to 0 to 1, because the probability, if it is 1, this is 100% true, this is 1, and if it is 0, there is it's 0, it's negative, and 1 is positive. You have you have the disease correctly, it is predicted as correctly, you have the disease. 0 is that you don't have the disease, so it is like that. And if your probability is like 0.2, also it would be like 0, and if it is probability is 0.7, suppose, it would consider at 1. So all the values would be converted into 0 up to 1, so that we can convert it into sigmoid function, sigmoid value, because logistic regression works up to 0 to 1, means 0 up to 1, nothing else. Okay, so then it works really well for low dimensional data features. If you have lower amount of features, like if you have 3 features and 1 class that you want to predict or identify or classify, if you have 3 or 4 features, then it would perform really well. For it says that how the lower the dimension of your data, the better it performs. It means that the lower dimension means less amount of features, like columns. Okay, so that is the most important thing, you have to get this. Then we have logistic regression optimization technique. So before understanding the optimization technique, let's understand the sigmoid functions a little better, a little elaborations compared to the previous one that I already talked. So the logistic regression, also known as the logistic function. So the logistic function is same as sigmoid function. It is also called sigmoid functions. What it does, it maps any real value to the range of 0 to 1. As I already talked about in the paint application, I showed you why it's 0 up to 1, because of probabilities. We can work perfectly with probability if the value is up to 0 to 1. Okay, we also have to know the gradient descent. What the gradient descent is like. To optimize the weights and minimize the loss functions, gradient descent is used, and gradient descent with respect to weights is calculated, and then weights are updated to the opposite direction of the gradient. And this is the equation, the new and the old minus learning rate. So what is the thing here? We need loss function. What is the important thing is loss functions. So if you don't understand anything, you can Google it later, but learn this concept. Gradient descent is a concept, and also artificial neural network also use gradient descent. It is really important to understand how this works. Okay, so let's go into paint application. Suppose we have a graph here, and gradient descent is like if you have a bowl here, and if we want to reach the bottom here, okay, and it can be like this also. If I draw it in the red, okay, so we want to reach the lower part. So this is the local, this is called the lower minima, but this is not the lowest position. Lowest position is when you reach here, okay. So you need to get into this lower position to get the highest performance or optimized performance. So if I just talking about here, suppose you are here now, you are learning something, and you need to change the weight. Weight is this thing, z is equals to w1 x1 and w2 x2 so on, and this is the weight, okay. So this is the weight. We need to first check our learning rate, and we need to make a slope here, and we're gonna check our performance, whether the performance is better or not. Then when it reaches this position, also you need to draw a slope here, and you need to change the weight here. Suppose here our weights is 10, and here you are changing your weight to 20. You are just checking at which position, at which value of weights you are getting the better performance. And when you are reaching this, suppose it is 30, but when you're reaching this, suppose it's 5, you are calculating it after reaching at this local minima or this lowest value. This is the place where your slope is 0, because you are just touching at the local minima, and here your learning rate will finish. You will be at your best. You learned everything. Now you're optimized. Now you are properly optimized. Here you are not optimized. Here also you are not optimized. Here also you are not optimized. You are just checking. You are just learning. Okay, so that's why it says that the new learning rate, the new data is equals to old data minus the learning rate alpha. Alpha is the learning rate, how you are learning, and its value can be 0.1. It means that you are learning very slowly. We know this also at C value. And when you are learning at very high speed like 10, you are learning very fast, okay. So it's performing like that. We need to just negate it in the old value. We need to just negate the learning rate, then we get the new value. So this is what the equation says, but mainly what it does is you need to just locate it, which is the lowest value, which is the lower minima. So this is the optimization. At the value of 5, we get the optimized result. Machine actually does this automatically by yourself. Automated, it is automated, you don't need to think about it, but this is how the gradient descent works. If the learning rate is smaller, then there would be like so many points. There would be, if I just take this, there will be this point, this point, this point, this point, this point, and this point. If the learning rate is very high, like C is equals to 10, then it should be here. It should be like 1 point is here, 1 point is here, 1 point is here. Done. Here you will find the optimized result. But if the learning rate is smaller, the rate of getting the better optimization, getting the probability higher would be better, because you will check every single point here, 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 here. Your learning would be better. Okay, so this is how you learn and adjust your weights. So we are just adjusting the weights of it, the coefficient, so that we can get the ultimate result or the highest value possible or the highest probability possible, so that we can optimize our function. Okay, so this is how the optimization works. So that's the thing of gradient descent. That's why I say to optimize the weights and minimize, we need to minimize the loss function. Okay, that's the thing we want. We need to minimize the loss. What we have in our model, we have some loss. We need to minimize the loss so that we can optimize the function or optimize overall output. We just need to optimize the weights. That's all. This is the thing that is most important. So gradient with respect to age is calculated, or it is differentiated. If you don't understand differentiation, that is the thing, that is the part where the differentiation or the calculus takes into place, where you need to differentiate with to find the local minima or the lowest minima. If you find the lowest minima value from the graph, you will get your optimized result. That is for sure. So that is the thing we need to optimize. The final one is that regularization. So what is this thing? So logistic regression can be extended to handle multi-collinearity and overfitting through regularization technique like L1 or L2 regularization or C value to control overfitting and underfitting. So what it says? Logistic regression can be extended to handle multi-collinearity. Collinearity means that one value is so linear, is so correlated with another value that it changes everything. If you change this thing, y value will be changed. If you change the x value, y would be changed significantly. So we make sure we don't do this. We need to make sure we handle this multi-collinearity among the x value or the feature value, the column value, and the result value or the ultimate value, the class level value. We need to make sure the collinearity is doing perfect work. Okay. And overfitting through regularization technique like L1 and L2. So logistic regression has some optimization technique, okay, or hyperparameter optimization called L1 and L2, and C value, which I already talked about, C value that can help overfitting and underfitting problem solution. So what does this overfitting and underfitting, what does that do? So let's talk about it, overfitting and underfitting. So what does that do? Overfitting is actually when your model gives so accurate output, but it doesn't give really good output if you just put it in new data. Suppose you have two data, which is x1 and x2, these are the feature vector, and based on that you will predict y. Okay, and suppose this is 5 and x2 is 5 and it gives 20, okay, as output. This is your training data. Remember, this is your training data. Based on x and y, it is differentiating, and your x2 value, x1 value is 10 and x2 value is 20, it gives 30. So it is depending on x and y value. If the x values and x2 value is greater, the output result would be 30. So you will train like this. But the problem is, the actual problem is when you feed a new data, okay, so it works really well for the training data, but it doesn't work for new data. Suppose this is 5, this is 50, and this is 100. Okay, it will show you some the junk values. It works well for the training values. It is pretty accurate, but when you feed a new data, it doesn't perform that much. Okay, it should be like 200 here, but instead of 200, it doesn't show that much. It shows only like 150. So as you can see, there is a 50 mark amount of gap. So the problem is that it doesn't perform well. The model is complex. Okay, but your data is simple. Okay, so that's the thing which is called overfitting. The underfitting is just the opposite, and you will understand it slowly, but this is the thing that you really need to understand. An underfit is the opposite of it. Your model is very simple, but your data is very complex. The complete opposite of it. Okay, so these are all the math intuition you must need to understand. So that's why it says that strong regularization helps prevent overfitting. If you have a strong regularization, you need to use a hyperparameter in logistic regression. It says C value, which is 0.1. It means that you are learning slowly to fit the model properly, so that it doesn't get overfitting. It doesn't overlearn. Okay, so if I show you a cat image, you can see the cat. If I test you with a cat image, if I say that what is this thing, okay, so you will answer no, this is a cat or this is a dog easily, because you are very complex model, you know everything. When I put everything, you will give very good answer. But when I give a new information, if a tiger, that you don't understand what it is. So that is overfitting. You have to understand this really perfectly, overfitting and underfitting. And when you are underfitting, it means that your model is very weak, you need to learn it faster. Then it called weak regularization. And when the weak regularization happen, you need to increase your C value to 10 so that you are learning properly. Okay, and C is equals to 0.1 is actually strong regularization. C is equals to 10 is weak regularization. So they are completely different thing. If you have overfit problem, you use strong regularization, you use C is equals to 0.1. But if you have weak regularization, you will C is equals to 10. So this is the optimization technique for logistic regression. It is really important and also the L1 and L2 for multi-collinearity, so that we can just identify the problem. And L1 and L2 also hyperparameter regularization technique for logistic regression. And C value is I already talked about to control the overfitting and underfitting problem. Based on the C value, we just check it if it is overfitting or underfitting, we can solve this problem. So as you can see, there are so many optimization technique and regularization technique in scikit-learn. This website is really important. And we have the penalty of L1, L2 elasticity. This is the optimization technique that you're going to use. Then we have a C value here and fit, intercept. These are all the optimization technique. Okay, so let's use those things. Okay, we have a solver also, like linear. If your data is very linear and is separable, you can separate the class. You can use those things. So let's code and understand. So let's open Jupyter notebook, and we have a new code. So here it is for logistic regression YT. Oh. So here you're gonna import, make sure you install it. Okay, you have to install it using the command line. Okay, pip install pandas, like import pandas as pd. Then what you need to do, you need to read the data. So read data. So what we can do, data frame is equals to panda dot read csv. If you just use tab, you'll see this thing. We need to use heart dot csv. This is our file name, our data set. So I think it is heart dot csv. Okay, csv. And data frame dot head. And if you use head and put a value 10, it will show you 10 data, as you can see. So these are all the features. So there's tons of features, 8 to 9 features. And AHD means that you will have a heart disease. Based on those features, chest pain, cholesterol level, the old peak, slope, many of them I even don't understand because I'm not a doctor. And sex one is, I think it's male, and for 0 it is female. So that can be different kind of thing. This is the thing that is we called encoding, because machine learning works better for the numeric value. So typically it says yes when the cholesterol level is higher. As you can see, this guy's cholesterol level is very high, 286, and the rest blood pressure is very high, and that is the thing where we say yes. But for the no, it is his cholesterol level is lower, his blood pressure is lower, and based on those other features, this is called the linearity. So some values dependent on this output. So what are the input features that affect the output of y? So AHD is the ultimate thing that we want to predict or classify. And as you can see, this is a multilinear because it is yes and no, only two classification. If I want to check it to make sure it is like that, we can do this. AHD, if you just like value counts, so value counts, let's check. As you can see, there are 164 no values and 139 yes values. There are a lot of things, and you can just copy this stuff to check other thing, like how many chest pain type here. Okay, in the previous video I also talked about it. There are 4 different types, which is typical, non-typical. These are the categories of the chest pain in the dataset, and non-original, non-typical, typical. These are all the things, and here data types. So this is numeric value. That's pretty beautiful. And we need to convert the chest pain. These are the string value. We need to convert it into numeric value. So what we can do? So first, let's check the dataset. So we need to remove the unnamed. This is the thing we don't want. df.drop, and we need to drop columns columns, drop it. So we can copy and paste, and we're going to assign it into our ultimate dataset. So then print, nice, it is clean. And now we need to just get inside the chest pane, this thing. So you can just copy this thing, there is no issues here. Chest pane, and we just need to convert this. This is chest pane, and it is always better to just copy and paste these lines, this column level, because I don't want to have any problem. As type dot categories. Okay, I want to just divide it into different subcategories, like 4 categories we have in the chest pane. Okay, and then what you can do, you can just copy this thing again, and here instead of as type, you need to convert it into cat dot codes. It will convert all those strings into different kind of code, like 0, 1, 2, 3 codes. Based on how many categories we have, 4 categories, it would be 4 different numbers. Okay, then if I just check it, and okay, category, okay, and now it should work, and you need to rerun it again. So if there is any problem, you need to rerun it, then it will solve your problem. Code chest pane, okay, if you just print it. So that's the problem, if you just copy and paste, you will have some problem. So make sure you use as type category, and then you can just convert it in categories into codes. We are just converting all those categories into code. So that is the thing that we want. Now as you can see, our chest pane is 0, 1, 2, 3. If I just want to check it, we can check this dot value counts. As you can see, we have 0, 1, 2, 3 up to 4 different types. So it is done. So now we need to check if there is null value. So how can we do that? df dot is null and dot sum. It will show you how many null values you have based on this category. So these are the column values, and in the CA column we have 4 null values. In this column, as you can see, we have 4 null values, and also at THL column, THL, we have null values. So this is the problem. So how can we remove this thing? So we just remove all of the null values. df dot drop na. Okay, so if you write df dot drop na, it will remove all the null values. Now as you can see, we have 297 rows, but previously it was 303. Almost 6 values are deleted, which are not null. Now to define x set and y set, because those are different thing. X is our features and y is our class, ultimate class that we want to classify. So we should differentiate it. So first one is df.drop. We need to drop some columns, and which column we want to drop from x value, which is AHD. So this is the class that we want to predict if this guy has diabetes or not, okay, based on this feature. So those features would be our x. That's why we are dropping only the column of class. This is the thing that is for y, so we need to drop everything from our x that says the column AHD. So this is the thing that we must remove from the x value, and also y, and here we will just take AHD. So y is the AHD, which this is the thing went to class, and x is the feature columns or feature vectors, whatever you want to say. So we need to drop it from x, and y is our prediction, so y should be in AHD. So only one column is y and all other is x. So if you want to check the x value here, so these are the x value. If it, as you can see, we don't have AHD. So if you want to check y value, and you will see yes, no, all of this stuff. Pretty simple. Now let's do this stuff, and we need to split the data. Split into train and test. Train test split. So if we just go sklearn train test split, we can just copy this code and we can paste this stuff. We don't need to worry too much. This is very common thing. For every machine learning model, we must do this stuff. So this is very common. So from sklearn.model selection, we need to import train plus split. Okay. And then we need one more thing from sklearn.model linear model import logistic regression. Okay, so these are the two libraries, really important. And also sklearn.metrics import accuracy score to check how accurate our model is. So here we need one more thing for pre-processing, which is sklearn.preprocessing import standard scalar. So if I talk about this, this is the pre-processing standard scalar. What it does, it converts any values in converts any higher value like 400 to 500 into very smaller number like 1, 0 up to 1. Okay, so most of the cases it will be like this. So how it calculates, z is equals to x minus u divided by s. So x is the value of individual value, like, so this is the individual value like 145. Okay, so 145 is individual column value, and just negate it with its mean divided by standard deviation. So if I go to paint application, you will see this stuff. So z is equals to this x minus u divided by standard deviation. Suppose you have a value 10, u is actually 10, 12 and 14. So our mean is 12. So if you want to calculate for 10, if you want to regularize it, or if you want to convert it into a smaller number, so 10 minus u is actually the median, which is our mean value, which is 12, and we need to divide it with the standard deviation. Standard deviation of 10 to 12 and 12 to 14 is only 2. So our ultimate result is minus 2 divided by 2, which is minus 1. So we are converting a big number 10 into a smaller number. It works for every single number. So this is how you just reduce the dimensionality, making a bigger number into a smaller number. So that's the thing. As you can see, these are the smaller number, but a max HR, that raised BP, cholesterol level, these are higher number. We need to convert into lower number. So that is why the standard scalar is really important. Put all of this stuff, and scalar is equals to standard scalar. We need to use this class, and here we're gonna divide everything. X train, this is the train data, and this is the scaled data. We need to convert to scaled data, and scalar dot fit transform, this is for the train data, and we need to pass train. So before I do that, you need to do one more thing, train test split. And train test split, you need to pass the y value and the x value at the test size, which is 0.3, or 30% of the data would be on the test, and random state like 21. It's a simple integer value that you can put, and it should be x train, x test, y train, and y test. So these are the values. Now we need to convert the into x train data into x train scaled, so that we can convert into smaller values, smaller transformation, so that we can make these values smaller. And taking the x train, these are the train values, the training data of x set. Okay, so that is the thing we are taking, and we are just using the x test here. Scaled is equals to scalar dot transform. Here we just transform the x test. This is the test data. We don't want to fit transform. Okay, we don't want to apply transform completely because we want to test it. So test data should be intact like this. That's why we didn't apply fit transform in the test data, only train. So here we're gonna put the x test. Okay, now it's perfect. And now if you want to check the value, you can check it. So it says we have some problem. We can't see the X test scaled. Seems that we didn't convert this column thal value into its numerical value. So we need to just fix everything here. So this is the thing that we need to copy. So after this column, you can use this stuff. So instead of this, we're gonna use thal, this column. So this is the thing that we're gonna use after this thing. So here we're gonna copy it into different category, and we're gonna pass, we just convert it into different category of codes. So chest pain, so instead of chest pain, it should be thal.cat.codes. And then as you can see, now it's converted into different code. For fixed it is 0, for normal it is 1, for 2, all of this stuff. So if I just check it here, after that, if I want to check that thing, we can do this. So it is for thal value. Okay, value counts. Let's check. So we have 3 different categories. So now I think it will work just fine. We're just removing any null value. We are dropping all the null value using drop.na, and separating X and Y data. And we also in the previously we also splitted the train data and test data, and we imported our model from logistic regression. For linear model, we just imported logistic regression, and accuracy score for measuring the accuracy of our model, and pre-processing to make sure all our higher number into lower number like 0, 1, 2 and 3, so that we can transform the X train data. And in the train data split, 30% of our data on the test size, and scalar.fit transform, so that we can convert into a lower dimensional number, or like a small number, and we're gonna fit the X train data. That this is only the training data, not the test. Test data is for testing our model, nothing else. And that's why I didn't use fit transform in the X test. We just use the test scale. So now I think it will work. As you can see, this is the data that is, as you can see, the numbers are very smaller now. This is the feature X train data. And if I just write here X test data, okay, these are also pretty nice. So logistic model is equals to logistic regression. I want to import our logistic regression, most important thing, which is random state is equals to 0, and here we can fit the model dot fit. What do we fit? X train data, X train scaled. So this is the data, X train scale. This is the training data we need to fit into our model. And also not only X value, we need to fit the Y value, Y train, and we're gonna predict. So logistic model dot predict, it has a function called predict, so that we can predict, and we're gonna predict the X underscore train scale value, and we're gonna get the logistic model dot score, so that we can get the accuracy score X underscore train scaled, comma Y underscore train. So we get 88%. So our probability is 0.88. So this is the accuracy score based on this model, because based on this train data set. Now let's work on test data set. So in the previous, as you can see, the 30% of our data are the test size, and 70% of the data are training data. So it works really well for training data, but we need to make sure it works better on the test data. Test data set accuracy test. Okay, so what we can do, this is the same thing. So we fit our model, just we need to just predict it using the test data set. So predict using X test data. Instead of train, it would be test scaled, and for accuracy score, this should be Y train, Y test data, and for X value, it should be X test scale. So this is the X value, and this is the Y test data. These are the test value. This is X test and Y test, because test data is the actual thing that you will get in your real life scenario. you will pass your test data and it will give you a score. So it's quite good. It is 0.8, almost similar to 0.88. It's quite good. Now let's make one more model, which is logistic model. This is for logistic model 2. Here we're gonna fit something. Let's fit this. Okay, and in that we need to change some functions, some hyperparameter optimization. Here random state is equals to 0, and we can pass some other data. So what we can pass here, we can first pass so many. If you press tab, you see so many things that we can configure. First one is the C value. I already talked about it. This is the regularization technique. If I make it smaller, it will learn smaller chunk by chunk. If I make the C value higher, this will solve the underfitting. If I if I add 0.1, it means that it will solve overfitting problem. If our model has some overfitting problem, we just you can use this thing. So if I put the C value 0.1, it will learn slowly, it will perform better. Okay, so this is the regularization technique, and we can add one more parameter, which is fit intercept. We can add an intercept, which is the C value where it cuts the Y. So this is the intercept. And also we can put the solver. What we can use, let me check what is the thing that we can use. Here C value fit intercept is equal to 2. We already use this. The solver is linear. So this is the thing we're gonna use so that we can differentiate the model linearity. We can separate the two different classes properly. It adds some linearity to the dataset. And solver, and one more thing that we can use, I think I totally forgot, what max iteration, for how many times you want to do this. For if you have multiple classes, you need to use multinomial, but normally in our dataset it's only yes or no. So yes or no, so we don't need to use that multilinear thing. So L1 penalty. Okay, so we need to add penalty. So let's check it out and add penalty here. Penalty is equals to L1. Okay, so then we're gonna fit our model, and then we're gonna check how it performs. We need to, we already fit this. Now we need to predict it. We need to predict it using the X-train scale value, and we need to check the accuracy of the score based on the, this should be test. This is not train, this should be test, and this is test data, and this should be test data. So let's check this out. I think penalty L1 was the problem. Okay, now it worked. So it should be penalty is equal to L1 or L2. It's a smaller case. L2. So if I just change the learning rate, C is equals to 10. Let's check. So it gives almost the same result as L1. C value suppose 6. So you can change those stuff and just check which gives the better solution. Elastic net, let's use for elastic net. This is the penalty. You can use this stuff and solver. Elastic net. So this is one type of hyperparameter optimization. So let's check it out. So I think I made some problem here. Okay. So, okay, this should be linear model underscore 2. This is linear model underscore 2. Y underscore red. And you're gonna write Y underscore red. So solver LBG supports only L2 and non-penalties got elastic penalty. So we need to change the penalty to L2 or L1. Then I already changed this logistic model 2 and logistic model 2.predict. And logistic model 1 is the previous model where we didn't add any optimization, but now we had add some optimization. As you can see, it has optimized. It has better optimization, 0.86. It was previously it was like for testing that is like 0.86, and for training data the accuracy is 87. It's almost close to the training data set. Okay, so our performance based on this test data is pretty good, 0.87. If we want to change the C value to 2 and penalty is L1 penalty, so I think it won't work. Penalty, you must use penalty L2, and C value is 10. Then we get this. If the C value is like 100 and it doesn't work, 0.2, same accuracy, almost same, so it doesn't work better than if I add 0.5 here and penalty L2 and fit intercept. It's almost the same. So this model, this is the highest performance that you get just tuning on those parameters, the penalty, the C value. So these are the hyperparameters that we have changed, and this is the ultimate result that we got. So this is the highest performance that you get from this data set. This data set is very small, so you shouldn't. So this data set is really small, so you shouldn't expect better accuracy than this. You can separate the data easily, linearly. Then you should use it. When you need scalable application, scalable model, and that can handle large amount of data, just use linear regression. This is the best thing that you can do. So that's all for today. I'll see you in the next video with more awesome, beautiful content. Till then, take care. Bye bye. I'll see you in the next video.